Welcome to my final project survey. My name is Fadel Matar and I'm happy to present my paper. This survey, I will be discussing the following papers. Deceptive deletions for protecting withdrawn posts on social media platforms. Incrementally updatable Honey passwords vaults. Recommendations for stronger, more usable passwords. IPv6 address correlations. Attacks on TLS encrypted traffic. The faults on our automatic speech recognitions, automated identification and classification of proprietary cryptographic primitives in binary code. Deletions for protecting withdrawn posts on social media platforms. Online social platforms are widespread with poorly phrased thoughts and personal information. Many users regret posting such content. Most platforms provide delete mechanisms for users to withdraw content, which social media users frequently use. Sadly, these deletions make users more vulnerable to privacy invasions by malicious actions who specifically target post deletions. The reason is simple. Deleting a post sends a strong signal that the post may be harmful to its owner. Several archiving services are already searching for deleted social media posts. Destructive deletions can also be detected at scale using powerful machine learning models. Here we can see a graph illustrating the process. What are the countermeasures? A new deletions mechanism that can select non-damaging posts, decoy posts, to be deleted along with the damaging ones is introduced to defeat the attack. These opposing goals create a minimax game between the adversary and the challenger that we call deceptive learning game. We also show challengers practical effectiveness on Twitter, where the bar is raised against strong adaptive adversary in automatically detecting damaging posts. The adversarial performance score drops to 65%, 42%, and 38% when the challenger has no access, restricted black box access, or black box access, respectively. As a result, we significantly raise the bar for malicious deletions on social media. Now we will discuss incrementally updated Honey password vaults. Password vault applications allow users to store multiple passwords and encrypt the vault with a master password. In practice, attackers can steal the vault's storage file and then offline guess the master password to compromise all passwords. Proposed solutions include Honey vaults. Attackers must switch from offline guessing to online verification in order to use Honey vaults. However, existing Honey vault schemes all suffer from intersection attacks when a previous version of the storage file, example a backup, is stolen. An attacker can offline identify decoys and destroy schemes. We propose an incremental update mechanism and generic constructions based on multi-similar password model. With our system, the attacker gains no advantages from the old storage and degenerates to an attacker who only knows the current password version. So what are the countermeasures? The study proposed a generic Honey vault scheme construction and incremental update mechanism. The update mechanism allows the vault scheme to resist intersection attacks in the case of multiple leakage. Our scheme relies on a well-designed multi-similar password model. Our evaluation on real-world data shows that our instance significantly improves security against traditional distinguishing attacks in the single leakage case. Our work may help other research areas. Password guessing attacks and password strength meters can benefit from incremental updated mechanism. Now we will move to practical recommendations for stronger, more usable passwords, combining minimum strength, minimum length, and block list requirements. Passwords can be made stronger by requiring minimum length and character class, prohibiting blocklisted passwords, and providing feedback on candidate password strength. However, there is little definitive scientific guidance on how to combine and congregate these mechanisms to best effect. The minimum length and character class requirements, block lists, and minimum strength requirements were all evaluated in two online requirements. Our findings lead to concrete policy recommendations that balance security and usability. We recommend policies that combine minimum strength and length requirements for high-value user accounts, while we advise organizations to use block lists. Using block lists does not provide additional benefits. Intrinsically, we found that character class requirements traditionally associated with stronger passwords may provide little improvement and may even reduce effective security against expert attacks. Recommendations. There are three types of recommendation. Composition policies. Less predictable passwords are encouraged by password composition policies. Composition policies can be used to enforce a minimum number of characters, classes, uppercases, lowercases, symbols, and digits, and a minimum password length. Block lists. Passwords should not be in a list of commonly used, expected, or compromised values. Quantifying password strength. It is possible to quantify the password strength of a password creation policy using guess numbers. Passwords predicted by particular guessing model can be enumerated in decreasing probability, or in the order that a commonly used password cracking tool would output guesses. We will discuss the paper of IPv6 address correlation attacks on TLS encrypted traffic via SEMISI heterogeneous graph attention network. A NAT masks IPv4 addresses, but IPv6 addresses can be easily linked to users' activity, compromising their privacy. Existing methods for addresses to user correlation are unreliable due to privacy mitigations. Even with these protections, an adversary could accurately correlate IPv6 addresses with users. We propose the same hand IPv6 correlation model to determine whether two IPv6 client addresses belong to the same user. The model uses SEMIC heterogeneous graph attention network using a large real-world dataset. We show that current techniques can only track target users and find unique users with 85% and 60% accuracy, respectively. However, same hand is 99% accurate. To mitigate IPv6 address correlation attacks, there are two types of countermeasures. Traffic obfuscations using random forged addresses or browser parameters to obtain random client. Attack chance reduction by using proxies. Speech recognition systems are used in as personal assistants, telephony surveillance, and biometric authentication. The increased privacy, the increased accuracy of neural networks has enabled widespread use of these systems. Recent research shows that speech and speaker recognition systems are vulnerable to input manipulations attacks, just like other neural network systems. Because of this, attacks and defenses against speech and speaker systems are very different from those against images. First, we systemize existing research and provide a taxonomy for future work. Then we show experimentally that attacks on these models almost never transfer. In doing so, we argue that more work is needed to provide adequate mitigations in this area. Countermeasures. Three types of countermeasures. Adversarial training. The defense involves training the model on samples. Using adversarial algorithms, the strategy has shown promise in the adversarial image space. Liveness detection. Considering the limitations of adversarial training, it is important to discuss detection strategies that have shown some success. Future direction may not guarantee success. An example of this is redesigning the feature extraction and processing state. Automated identification and classification of proprietary cryptographic primitives in binary code. The continued use of proprietary cryptographic and embedded systems, from physical access control to telecommunications to machine authentication, hinders black box security evaluation efforts. Manual inspection, even with heuristics, is time-consuming when locating and classifying the algorithm in large binary images. Countermeasures. Despite the widespread availability of royalty-free open-source cryptographic primitives and implementations, proprietary alternatives persist in many industries, particularly embedded systems. Because these primitives are undocumented and proprietary, locating and classifying them in large binary images takes a lot of time and effort. Identify unknown cryptographic algorithms support large real-world firmware binaries and not really peripheral emulation to overcome the obstacle automatically. Thank you very much for listening, and I apologize for any mistakes while reading. Thank you very much.